there are two formulas that we need to know for our financial interest problems. And one of them is A equals P times the quantity 1 plus R over N raised to the NT power. This is the formula when we are compounding money, compounding interest, N times per year. N times per year. So you might remember that. Hopefully you do remember that, because that's a pretty major formula for college algebra. The other one is when your interest is compounded continuously, and that's A equals P times E raised to the RT power. So R times T is in the exponent. This is called the formula for compounded continuously. Compounded continuously. And it comes from, I would just want to show you where it comes from now that we're doing calculus. It comes from our formula on the left. If we take P times 1 plus R over N, raise it to the nth power, we'll just say our time is 1 year right now. And I say, well, let's look at the limit as N gets really, really large. So continuously means that the number of times it's compounded would almost be an infinite number of times. So not just 12 times, which would be monthly, not just daily, which would be 365, but constantly, continuously. So your N would be an infinite number of times. So we're looking at the limit as N approaches infinity of P times 1 plus R over N raised to the nth power. Now P is a constant, it's a multiplier, it's a scalar. So I can take that scalar out in front of the limit. And now I just have 1 plus R over N raised to the nth power. And then what I'm going to do is I'm going to take that nth power and I'm going to divide by R, but I'm going to raise it to the R power. And that's going to make it unchanged, because a power to a power you multiply. N over R times R is still N. So I haven't changed it, it's still N. I've just changed what it looks like. Now 1 plus R over N, if I say let's let N over R equal X, then I have P times the limit as N approaches infinity of 1 plus, if N over R is X, R over N is 1 over X, N over R is X, and then that's raised to the R power. Well, what is this right here? What is this? What is that? That right there is E. That is E. So we have P times E. Let me make P gray again. We have P times E. This right here, the limit as N approaches infinity of 1 plus 1 over X raised to the X power. Now I can change this to X as X gets really, really large, right? That right there is E from the previous video. And then we have raised to the R power, and then I'm going to bring back that T. And that is where our compounded continuously formula comes from. Because this is a video, you can completely rewind, slow it down, watch it over a couple times if you're interested, but that's why they call E the banker's constant. Okay, now that we have our two formulas, you're creating a trust fund for your nephew who was just born. You deposited $12,000. You're very wealthy. You deposited $12,000 in an account with instructions that the account be turned over to your nephew on his 25th birthday. Compare the balance for each situation and determine which account you should choose. 7% compounded continuously, 7% compounded quarterly, 11% compounded continuously, or 11% compounded quarterly? Well, we want to be able to justify which is the best account, so we're going to do all of these calculations. So what I'd like you to do is practice using those two formulas, press pause, and see if when you come back, if you were able to use those formulas properly. Okay, welcome back. If you have not pressed pause, please take the opportunity to do that. Okay, we have 12,000 times E raised to the 0.07 times 25 power. And that gave us a balance of $69,055.23. Not too bad, not too bad. Might jump on that, but let's think about compounded quarterly. We'd still have an initial principal balance of 12,000 multiplied by 1 plus our rate is 7%. Compounded quarterly means N would be 4. There's 4 quarters in a year. And then 4 times 25. So N times T. We put that into our calculator and we get approximately $68,017.87. So far, 7% compounded continuously is a little bit better. 11% compounded continuously, well, the rate is higher, so that tells us something. 12,000 times E, because we're talking about PERT, raised to the RT power. The rate is 0.11 and 25 years is the time. We put that into our calculator and holy cow, $187,711.58. Winner, winner, chicken dinner. But we need to be able to back it up by comparing it to 11% compounded quarterly. So that's 12,000 times 1 plus 11% divided by 4 times a year raised to the 4 times 25 power. That's going to be approximately $180,869.07. So we can see that this is the best account, and that's because it has a higher interest rate on the interest, and it's making more money because the account is also evaluated most frequently, which is continuously. So it's got 2 things working for it: higher interest rate and compounded continuously. That compounded continuously is going to bring us more money. Okay, the effective rate of interest corresponds to the nominal rate of 6% per year compounded annually, quarterly, and monthly. That's what we want to find, the effective rate of interest corresponding to the nominal rate of 6% per year. The nominal rate is the stated rate. It's the stated rate. It does not reflect interest earned. Okay, it does not reflect interest earned. So your effective rate is equal to what's actually happening. So 1 plus R over N raised to the N power minus 1, that's your effective rate. We want to know the effective rate. If the stated rate is 6% per year, what would the effective rate be? Well, annually, it should be the same, 6% per year. Let's check it out. So our effective rate, R sub EFF, is equal to 1 plus, forgot the 1, 1 plus 0.06 for your nominal rate over 1 for annually. So annually is once a year, raised to the 1 power, because that's once a year, minus 1. So 1 plus 0.06 minus 1 is 1.06 minus 1, which is 0.06, which is 6%. So that's annually. Let's try quarterly. So quarterly, the effective rate is equal to 1 plus 0.06 divided by 4 for 4 quarters in a year, raised to the 4th power, minus 1. When I put that all into my calculator, I should get 0.061364. Multiply that by 100, and we get 6.1364%. So we go out 3 decimal places, 6.136% versus the nominal rate of 6%. So your rate is a little bit higher when you're compounding your money 4 times a year versus when you're compounding it just once a year. Now let's look at what happens when it's monthly. So here, let me just highlight that change. So what's happening when it's monthly? Monthly, our effective rate is equal to 1 plus 0.06 divided by 10 raised to the 10th power minus 1. So that should be, since they're looking at our money more frequently, and I put 10, but there's 12 months in a year. I bet you were wondering how long I'd go with that one. No, I caught that one. So our effective rate is about 0.0616778. I'm going to multiply that by 100 to make it a percent, and I get 6.16778%. 3 decimal places says 6.168% versus that 6% nominal rate. The more frequently they look at your account, the higher the actual rate of interest. So the annual rate is 6%. That's called the nominal rate. It's your annual interest rate. But your actual interest rate, if they compound your money more than once a year, this is just once a year, so that equals the nominal rate. But 4 times a year is higher, and 12 times a year is even higher than that. Okay, one last formula, future value. That's your A. We already know how to use this formula because we've used it quite often. Present value is when we solve for P. So P is our principal. We're going to solve for P. And if you take this equation and solve for P, you get A divided by 1 plus R over N raised to the NT power. That's your present value. If we want to solve this problem where an investor is purchasing a 12-year certificate of deposit that's called a CD, pays an annual percentage rate of 8% compounded monthly, how much should the person invest in order to retain a balance of $15,000 at maturity? So they want to know, what present value do I need if I end up with $15,000? The interest rate is 0.08, which is 8%. Compounded monthly would be divided by 12, and then that's raised to the 12 times 12 power. Why 12 times 12? 12 for monthly, and then 12 for 12 years. When I put that into my calculator, the present value, drum roll, press pause, is $5,761.72. That's what he needs today to end up with $15,000 in 12 years.